All right. Good morning, everyone. How are you? Great. Good. Good. For the recording, this is again the second in possibly a series of two lectures that I'm giving for a live studio audience. Okay. So yesterday in the last recording, we discussed the magnetic field created by a infinite, what we euphemistically call an infinitely long wire. And again, as I think I mentioned yesterday, what we are really talking about is calculating the electric field or measuring the electric field at a distance from a current-carrying wire, and that distance is understood to be very small compared to the length of the wire. And we've talked about this before, and I used exactly the same example when I talked about the electric field of a long straight wire. The example I used was the power lines that run down your street, and you're about 10 meters below the power line, but the power line itself is hundreds of kilometers long, and so that, to a very good approximation, you can treat that, in fact, to an incredibly good approximation, you can treat that as an infinitely long wire. We talked about the electric field back in the day, and then yesterday the expressions I said. Yesterday we did the infinite wire. Yesterday we did this expression. And so it was mu naught I over 2 pi r, where r, as always, is how far away you are from the wire carrying this current. Mu naught is the permeability of vacuum. Actually, I was just doing some reading and some researching just the other day and discovered that modern terminology, we no longer refer to this in modern usage as the permeability of vacuum. Modern usage is to simply call it the magnetic constant. And epsilon naught nowadays is, the new standards are to simply call it the electric constant. And there are reasons behind it, and they're not terribly relevant here, but being, as you know, a physics professor who I have my pulse, not my pulse, I have my finger on the pulse, that's the metaphor I want, on cutting edge modern day up to the second development. Okay, I'll stop now. All right, and so this was the expression, this is the magnitude of the magnetic field, and then I said the direction. So if you have a long straight wire like this, there's your current. There's your wire, and just for the sake of it, I'll reverse the direction just so you see it. So if your current, your positive conventional current, happens to be flowing that way, you determine the direction of the current using the right-hand rule, and the result turns out to be that your magnetic field lines actually encircle the current rather than pointing toward or away from it. And so one way to draw, I did it differently yesterday. Here's another way to present the diagram for the magnetic current loops. Although I'll use a pen that you can actually see. Right, and so the broken loop there is just supposed to indicate that that's behind the wire, right, behind the whiteboard. And so the direction is determined by grabbing the wire with your right hand, thumb pointing in the direction of the positive conventional current, and then you curl your fingers around, and whatever way your fingers curl around, the magnetic field line curls around in that same sense. Okay, so in this case, behind the board, my fingers are pointing downward. Directly below the wire, my fingers are pointing out of the board. directly in front of the board, they're pointing upward into the board at the top, and so on. And so I would try to probably draw, it would look something like that. And I don't know if that's any clearer than any of the diagrams I made yesterday, but this is an alternative form that you often see. So that's our magnetic field. But again, the whole point of this is that they are circles they circle around what the current, with the current at the center of this circular magnetic field line. So, any questions on that? Okay, the thing that I want to draw your attention to is this factor of 2 pi there, and I did not, and I will not even approach showing you the mathematics behind the derivation of this particular field function, and it is a function, by the way. The field strength depends on how far away you are from the current. It's incredibly complicated where this expression comes from, and it's not terribly useful for our purposes. But I do want to make one comment about that factor of 2 pi, and I could even extend it to 2 pi r. In some contexts, what does 2 pi r represent? No, not area. The circumference, correct? Yes. I know it's a low biorhythm day. It's Thursday. It's not a good day. Yeah, and don't worry, Christian. You're not on the video, so no one knows that you, Christian, were the one that said that 2 pi r. Christian said was the area of a circle, because Christian said that, but Christian wasn't on the video, so nobody knows that it was Christian that said. You know, the thing now for you watching the recording, the thing you've discovered now, which you only see it when I'm lecturing live to people, the thing you haven't seen in any of my recordings before. Now you've discovered that I am in fact a jerk. Now, you were supposed to laugh at that. I hate you all. All right. No, they're very nice people, especially Christian. Okay. Oh, let me show you Kristen. No, I'm kidding. Yeah, Chris, question. Yeah. A magnetic field can exert a force on a charged particle if the charge is moving. Yes. Okay, so for the recording, the question was, so the current creates this magnetic field, which in turn creates a magnetic force on some other charge that might be moving nearby, so velocity v, so qv cross v, right? That's the magnetic force. The question was, are there any other forces that would act on this charge because of this current, because of the fact that it's flying near a current, other than the magnetic force? Any thoughts on that? What do you guys think? Do you identify any other possible forces or sources of forces? Sources of forces, yeah. Go ahead. Why would there be an electric force? Sure, yeah, absolutely. Because the current is made up of charges. So yes, absolutely. There is definitely an electric force on this charge in addition to the magnetic force. And what direction would that magnetic force be pointing? I'm sorry, the electric force, sorry, the electric force. Coulomb's law, folks. Electric force on this due to these charges. You're right. Yeah, straight up, sure. Absolutely. right? Positive charges in the wire, positive charge here, upward. Now, the reason for your confusion, I suspect, let me offer up a suggested reason for the uncertainty in your faces. I shouldn't say confusion, uncertainty is you might be thinking, well, except Kevin, we're pretending that they're positive charges moving, but in fact, in reality, they're negative charges moving the other direction. And while that doesn't matter for the magnetic force, surely that matters for the electric force. And that's a very good question. The answer is very subtle, and so I'm going to decline to go into it. But suffice to say, it's a very subtle question. Yeah. Yeah. No, I don't think it was. I don't think it would. Well, let's see. What's the direction of the magnetic force on this thing? At the location that I've drawn it, the magnetic force. I should see. I should see a room full of this. I'll give you a pro tip. Remember that the magnetic force must always, always, always be perpendicular to both the velocity vector and to the magnetic field vector. So, V cross B, right? So V is pointing that way. Up here, what direction is B pointing? Up here. Okay, I'm going to pause the recording and let you guys discuss it. Okay, we're back, and it looks like my gang here has reached a consensus. So the two questions: what is the direction of the magnetic field vector at the top? So let's start with that one. So straight up, okay, into the board, out of the board. Great. So much for consensus, huh? Okay, so. And I'm not in the least surprised that you're struggling with it, because it is difficult to work around. So wire's going like this, okay, and I think I'm going to need another hand, as I did the other day. Be careful there, okay. Women are the future. I agree with that. Okay, do you want to stick your head and say hi to the camera? There it is, and that's Melinda, that's right. Terrible with names. Okay, so, oh, we're going that way. Actually, we've got to switch sides. Okay, and let me get in the camera a little bit. Okay, so the current is flowing that direction, yeah? Okay, so grab the wire with your, and until you get really good at this, I encourage you to actually get a real wire and really do this. Until, right? Okay, so anyway, grab the wire with your right hand with your thumb pointing in the direction of the positive current flow. And then curl your fingers around. And when you want to know what direction the field is pointing, you got to put your fingers at the location in space where you're trying to determine the direction of the field. And so in my case, the question is up above the wire. So I curl my fingers around until they're up above the wire. And now they're pointing into the board. Okay? Good. All right, I think we're good. Thank you, Melinda. All right. And so the magnetic field up there, so I would draw it like that, right? Right. Okay. So with that done, now what direction does the magnetic force point as a consequence? Oh, good. Sarah's here to take over the class. No. Which way, guys? I'm sorry. Straight upward? Okay, so V is pointing that way, B is into the board, V cross B, yep, well done. Good, good, good. And, okay, so the net force is upward, so there's that. All right. And actually, Sarah, my students asked me a question I want to discuss with you later. What? Well, the question was, no. So positive, for the recording, I'm talking to Sarah Sefri. Say hi to the camera. No, you're on recording. Positive charge, positive current flowing. Electric field, what direction does it point? I mean, the electric force on this. Because it's really negative charges moving. The positive conventional current, but it's really negative charges. Actually, I think I know the answer. There is no electric force, is there? Because okay, the question was what is the direction of the electric force here, and the answer is 0, right? Because there's no net charge, right? Okay, yeah. I was puzzling through it until I started talking to you, and then as soon as yes, exactly.
Anytime you have questions, you talk to me.
I always do, Sarah. Yeah, okay, and the answer is right. So I made a mistake. Thank you, sir. I made a mistake earlier. No, there is no electric force here, because in order to have electric force, you have to have a net electric charge, right? And even though our conventional current is moving, that doesn't change the fact that there's still equal numbers of positives and negatives. And so there's no net charge. There's still no net charge in the wire, and therefore no net field, and therefore no electric force. So it's only the magnetic force. And so the answer to your original question, Cliff, was the force is going to point upward, and so our charge will actually curve upward like that. It'd be in kind of a hyperbola thing, as it turns out. Because, of course, as it gets farther away, the strength of the magnetic field and therefore the magnetic force gets weaker, yeah? As you get farther away from the wire. So, okay, so there's that. Questions? If what was negative? If this is negative? Okay. If this was a negative charge, so if it's still moving the same direction, what's the direction of the force on it? Straight downwards, yep. Yeah, negative charge, just like in electric forces, negative charges experience forces opposite the direction that positive charges would experience, yes. Okay, good. Okay, well, this was meant to be a recording on a different topic, but so this one's gone on long enough, so I'm going to stop this recording here and start a new one on the topic that I actually planned on talking about today. But this was good.